Hello everyone, I'm Javed Akhtar Mondal. I am a PhD scholar in the Department of Physics of IIT Kanpur. I am working in the Quantum Measurement Lab under Professor Shaikat Ghosh, and I am also a recipient of Prime Minister's Research Fellowship. So I also have an website of my own, so where you can find about my research work. I will put the link for the same in the description box. And regarding that Prime Minister Research Fellowship, for the teaching requirement, I will upload some videos regarding previous year questions paper that appeared in various entrance examination like JEST, GATE, NET, etc. So people preparing for this exam will be benefited. So let me introduce, let me write my name here. So I'm Javed Akhtar Mondal, and I will solve question paper from like GATE, JEST, NET, etc. and all this. So I will try to solve problems by explaining the theory behind it little bit so that similar kinds of problem can be easily tackled. And first I will start with problems from quantum mechanics. So while explaining, so if I say something wrong or there is some calculation mistake, so I will put the correct one in the description box below. So let's get started. So let's start with problems that appeared in JEST 2018. So this is our first problem. So it states that a one-dimensional harmonic oscillator which has mass m and natural frequency of oscillation omega. So it is in a state psi such that the only possible outcome of an energy measurements are E0, E1 or E2. So where En is the energy of the nth excited state. So if H is the Hamiltonian of the oscillator such that, so this is given, then we have to find the probability that the energy measurements yield E0 is 1 half, 1 by 4, 1 by 8 or 0. Okay, so let's start. So we know that for a one-dimensional harmonic oscillator, the operator, Hamiltonian operator, is defined as p square by 2m plus half m omega square x hat square, where p hat is the momentum operator, x hat is the position operator. So these are operators. And for that Hamiltonian, we know that energy eigenvalues are h cut omega n plus half. So what is E0? E0 is h cut omega by 2. This is ground state energy. And E1, the energy of the first excited state, will be h cut omega 1 plus half. So this is 3 by 2 h cut omega. So this is first excited state. Similarly, E2, the energy of the second excited state will be 2 plus half h cut omega. That means 5 by 2 h cut omega. Second excited state. Now, what could be the possible state? So here the energy measurement only yield E0, E1 or E2. That means only either ground state or first excited state or second excited state are possible. So we can write our state as C0, 0, C1, 1 plus C2, 2, where N represents the nth excited state and Cn square. So let me write it in a clear way. And Cn square, this represents the probability of nth excited state. So psi can be either it is a superposition of 0, 1 and 2. No other states are possible because energy measurement can only give us either E0 or E1 or E2. Now can C0, C1 or C2 have any arbitrary values? Well, it can't, because we know that the wave function should be normalized. So we have a constant that psi should be 1. So if we calculate this, so we will get C0 star 0 plus C1 star plus C2 star 2, where stars represent the complex conjugate of C0, C1 and C2. And we have psi, so C0 0, C1 1 plus C2 2. So this should be 1. So if we C0 star C0 and plus, first let me write, then I will explain this thing. C1 star C1 plus C2 star C2. So why I am writing this? Because we know that n is 1 and m should be 0, where n is not equal to m. So this comes from the orthonormality condition. So these are orthonormality condition of energy eigenstates. So we can write this as C0 mod value, C1 square mod value plus C2 square mod value. This should be 1. So this is our first condition that we get. So this is our condition number 1. And now we have condition that psi should be 3 by 2 h cut omega. So we have to evaluate this expression. So what is h psi? H psi. So let us expand this. So psi, we know C0 0, C1 1, C2 2, and H is an operator obviously. So C0 H0, C1 H1, C2 H2. Now this 0, 1, 2, these are the eigenstate of the Hamiltonian. So that means if I apply Hamiltonian on nth energy eigenstate, we will get eigenvalue En, and we will be returned with the same energy state. So in that way, we know H0 will be E0 0, H1 will be E1 1, H2 will be E2 2. So we can write this as C0 E0 0, C1 E1 1 plus C2 E2 2. So psi H psi will be C0 star 0, C1 star 1, C2 star 2, and we have this term as C0 E0 0, C1 E1 1 plus C2 E2 2. So now we will again use the orthonormality condition of eigenstates. So using this, we will get this term as C0 mod value E0, C1 square mod value E1 plus C2 square mod value E2. So this is given as 3 by 2 h cut omega. So this is another condition. Now we know this E0, E1 and E2, and we can put this. So this will be h cut 2 C0 square plus 3 C1 square plus 5 C2 square, and this side we have 3 by 2 h cut omega. So simplifying more, we will get C0 square plus 3C1 square plus 5 C2 square, and this is equal to 3. So this is our second condition. Now we have given another condition, so which is, let me write the condition first. Psi h square psi, it should be 11 by 4 h cut square omega square. So like the previous way, first we have to calculate this. So we have already calculated h psi, and h psi comes out to be C0 E0 0. Okay, so let me write in short way. I1 2 3 Ci Ei I. So if I again apply this Hamiltonian operator, so we can write this as hi, and this hi we know already, so this we can write this as Ci Ei I. So this I1 2 3 Ci Ei. So again this hi, it will give us Ei I. So we can write this in this way. So this is our h cut square psi will give us this value. So if I again apply a get, then we will get so let me write this as j1 2 3 cj star j. So this corresponds to our psi, get psi, and we have our h cut square psi as I1 2 3 Ci Ei square I. So evaluate this. J1 2 3 I1 2 3 Ci Cj star Ei square, and we have Ji. So we know from orthonormality condition that Ji is delta Ij. So we can write this as I1 2 3 Ci square Ei square, and we know these values. So C0 square into h cut square omega square by 2 plus C1 square to 9 by 4, sorry, this should be 4, h cut square omega square, and another term we have C2 plus 25 by 4 h cut square omega square. So this psi h cut square psi, it is given as 11 by 4 h cut square omega square. So we have another condition, which is C0 square plus 9C1 square plus 25C2 square, this is equal to 11. So this is our third condition. So to simplify, let us write this C0 square as A, C1 square as B, and C2 square as C. So first condition we have A plus B plus C. This should be 1. So that is our first condition. Second condition we get A plus 3 into B plus 5 into C, that is equal to 3. So that is our second condition. And third condition now we get is A plus 9B plus 25C. So this is 11. So these are the three conditions which we have to solve, and if we solve them we will get A, B and C. That means the probability of being in ground state, probability of being in first excited state, and probability of being in second excited state. So how can we solve this? So we can solve this by matrix method. So we can write these three conditions as this. So we have a matrix. So we can write all these three constant in this matrix form. So it is 1, 1, 1, 1, 3, 5, 1, 9, 25. A, B, C. So why I am writing this in this format? So it is easier for, like, so suppose we have another one, another like third excited state. So we will have 4 constant, like, and 4 variables. So in this similar manner we can construct a 4 cross 4 matrix, and if we do the inverse of the matrix we will get all the probabilities of different excited state. So it can be generalized, like for any number of excited state. So I'm now not solving this in detail. So what you have to find the inverse. So if we call this matrix as M, so, and call this as X, and let us call this as N. So we have to just find that M inverse. So here we have this. So how we are getting this? Because we have mx equal to n. So if we multiply both sides by m inverse, then we can find x as m inverse n. And inverse, we know that inverse of any matrix is defined as adjoint of that matrix by determinant of that matrix. So we can calculate this adjoint and determinant, and from that relation we can calculate x, and it turns out that for the given matrix, A is 1 by 4, B is 1 half, and C is 1 by 4. So now what is A? A is C0 square. This is 1 by 4. B is C1, 1 by 2, and this C is C2 square. So that is 1 by 4. That means the ground state probability is 1 by 4. First excited state probability is half, and second excited state probability is 1 by 4. So in the question we are asked to find out the probability that the energy measurement yields E0. So you have to find the probability of the ground state. So ground state probability, that means we have to find C0 square, and it's turned out to be 1 by 4. So option B is the correct answer. So in the similar manner, like you can solve for different constants. So this is the concept, general concept, and in this way you can solve for more number of excited state or for different conditions. So let's jump into the second problem. So what it is stating? So it is stating that we have two canonically conjugate operators x and y, and their commutation relation is given as this. So first we have to know what is canonically conjugate operators. So like position and momentum, these are canonical conjugate operators. So and they satisfy this commutation relation. So what does this commutation relation signify? It signifies that these two the observable corresponding to this operator, like this has position observable and this has momentum observable. So we cannot simultaneously observe these two. So suppose if we have two simultaneously measurable observable, then we will have a commutation relation like this. So this is 0 for two observable that are simultaneously observable, but we know that we can't measure position and momentum simultaneously. So that is why their commutation relation is not 0. So we have like these two canonically conjugate operator x and y, and they have this commutation relation. So where I is the identity operator, and we are given x as alpha 11 q1 plus alpha 12 q2, and y as alpha 21 q1 plus alpha 22 q2, where alpha ij, these are generally complex numbers, and these observables, these operators q and q1 and q2, they are also not simultaneously measurable, so they also satisfy a non-zero commutation relation, and it is given as zi. So we have to find the value of this alpha 11 alpha 22 minus alpha 12 alpha 21. So we have to find this. Now before proceeding, first recall some general rules of commutation. So we know, so these are general rules. Suppose A is a operator, then A must be 0, because these two operators corresponding to same observable, and we know that, so it is quite straightforward that this should be 0. So in this way, like we have q1, it should be 0, and we have q2, this also should be 0. So this is first rule of commutation, one rule. Another rule is like this. So suppose we have a scalar multiplied with the operator a and b, then we can write this as a b this. So this is another rule. And third rule is like, so we have this, and so we can write this as a b plus a c. So where a b c, these are scalars. So if we follow these rules, then we can calculate this x, the commutation relation of x and y in terms of q1 and q2. So this is given as I h cut I. Also we can write down x as alpha 11 q1 plus alpha 22 q2. We have y as alpha 21 q1 plus alpha 2 to q2. This one should be alpha 1 to q2. Yeah, fine. So this is I h cut I. So following these three rules, we can write this as alpha 1 1. The first term should be 0 because first term contain this commutation and it is 0. Similarly, so second term will be alpha 1 1, alpha 2 2, q1 q2, and the third term, like permutation of these two, it will give us as alpha 1 2, alpha 2 1, q2 q1, and the last term, it will involve the commutation relation q2 with q2. So similarly, it should also be 0 because this represents to same observable. So this is 0. So in the right hand side we have I h cut I. Now we know that in the question it is given that q1 q2 is zi. So q2 q1, it should be minus zi, because another rule is AB permutation should be equal to minus of BA. So this is fourth rule. So using this, from here we can get alpha 1 1, alpha 2 2 into zi minus alpha 1 2, alpha 2 1 into zi. Minus is taken care here, and we have I h cut I. So from this we can get alpha 1 1, alpha 2 2 minus alpha 1 2, alpha 2 1 is equal to I h cut by z. So in this question we have to find this alpha 1 1 minus alpha 1 1, alpha 2 2 minus alpha 1 2, alpha 2 1, which we find out to be I h cut by z. So our correct answer is this one. So this is our answer. So what is our take home message from this question? So it is that if we have two observable that are simultaneously measurable, then the operators that represent those observables, they must commute. And if we have two observable which cannot be simultaneously measurable, then the operator corresponding to those observable, their commutation relation is non-zero. Okay, now let's move out to third problem. So the question states that we have given a normalized eigenfunction and eigenvalue of the Hamiltonian of a particle confined to move between 0 to a in one dimension. So this is our eigenfunction and this is eigenvalue. So we quite know well that this corresponds to an infinite potential well. So the potential well should be like this. So this is our x dimension, this is x0, and this is x equal to a, and in this region, we have potential infinity, and in this region also we have potential infinity. So infinite potential, that means particle cannot move in that direction, both direction. So if it is an finite potential well, so then there is a probability of tunneling and all that. But for infinite potential well, there is no probability of tunneling. So the probability of finding the particle at x equal to 0 and at x equal to a, probability of finding the particle is 0. Same for this region and this region. So particle can only travel in this region, in this x equal to 0 to a. So if we look closely, so there is a mistake in the question. So the normalized wave function should be this. So like you can calculate the normalized factor if psi n is this, n psi x by a. So from the normalized condition, we have to have this between 0 to a, this should be 1. So if you do the integral, then a comes out to be root over 2 by a. So there should be a factor of root, so which is I think printing mistake, and we have the normalized energy eigenvalues to be n square pi square h cut square by 2m, where n represents the excited state. So n equal to 1 means this is ground state, and 2 means fast excited state, and so on. And similarly for n3, 4 and all this. So this is eigenfunction and eigenvalue. Now suppose that the question states that the state of the particle is this: a sine pi x by a into 1 plus cos pi x by a. So here is the, like, we have to find the value of a by normalizing this wave function. So for any quantum mechanical problem, if the state is given, first you have to ensure that the state is normalized, because psi square represent probability and summation of probabilities should be 1. It should not be greater than 1. So that is why you have to have the wave function to be normalized. So we have to normalize this wave function. This is confined between 0 to a. This we have to ensure that this is 1, and from that we can find the value of a. So you can do this by standard integration, and so it will be a little bit messy. So you can do this by applying some trick. So if you do this problem in bracket notation, then it will be easier. So let us manipulate the wave function that is given. So we can write this as a let's multiply this sine pi x by a plus sine pi x by a cos pi x by a. So we can write this as a. Let us multiply this by root over a by 2 and root over 2 by a, and so this is 2 by a sine pi x by a and root over 2 by a sine pi x by a cos pi x by a. So why I am doing this? We are doing this because we know that the eigenfunctions is in the form of this. So we can write 1 as psi 1 x, and in bracket notation we can write 2 as psi 2 x. So if you observe this, this is our psi 1 x, and the second term, if we you can do a little bit manipulation, then multiply this by half, and this will be 2 sine a cos a. So we can write this as sine 2a. This is standard trigonometric result. So it will be sine 2 pi x by a, the second term. So from this we get psi x as root over a by 2 into a. This one is our psi 1 x plus half into psi 2 x. So this is a standard trick or you can do this by this integration, but it will be a little bit hectic. So in bracket notation we can write psi. So this one is in, this expression is in position basis, but in bracket notation when we write, there is no basis. So if we project this in position, so it will be in position basis. So in bracket notation we can write this as root over a by 2 into a. Let us write this as 1 and half 2. So this is our given wave function. So now we can find a very easily. So what is the process? We know psi should be 1 because of normalization. So we can write a into a by 2, and this psi would be 1 plus half 2, and from second term we will get 1 plus half 2. Now since this 1 and 2, these are energy eigenstates, that means they are orthonormal. This you have to keep in mind always. So these are orthonormal. So from here we can write this as, this term will be 1, and 1k 2 bra, it will be 0. Similarly this term will be 0, and here will be another term. So if you calculate this from here, okay, sorry, so here should be a square. So a square into a by 2, this will be 5 by 4. So from here we will get a to be root over 8 by 5a. So if we put this, then psi will be root over a by 2 into root over 8 by 5a, and we will have 1 plus half 2. So this a will be cancelled out, and we only have this term 2 by 5 1 plus 1 by root 5 2. So this is our wave function. So the state of the particle is this. This is the state in what? In bracket notation. Now the question states that if the energy of the particle is measured, the probability to get the result h cut square pi square by 2m square is x by 100. So you have to find the value of x. So this is what? This is the energy of the ground state. So pi square h cut square by 2m square, this is the energy of the ground state. That means we have to find the probability for the state to collapse in ground state. That means in state 1. So what does this coefficient and this coefficient signifies? So it signifies that suppose we measure the energy of the particle, so to get so the probability to get the ground state energy is square of this coefficient. And also the probability to get similarly this 1 by root 5, the square of this term, it will represent the probability for the state to collapse in fast excited state. So in the question we have to find the probability to get the ground state energy. So the ground state to the probability is 2 by root 5, the square of this. So it is 4 by 5. So we have to we have to find this as x by 100. So if we multiply this by 20, so we are getting 80 by 20. So this is the probability of the state psi to collapse in ground state energy if we measure energy. Sorry, ground state energy eigenfunction. So the value of x, this should be 80. This value is 80.